So we said that if we want, we can list the non-minimal couplings that we can add without introducing parameters of negative dimensions in units of mass. Let's list them all. So you may have a constant times r, the Riemann tensor, mu rho sigma, contracted with chi. Since chi is symmetric, can only be contracted mu rho nu sigma. Cannot contract with the mu nu. Plus a2, there is a non-minimal term with Ricci. Actually, there are two non-minimal terms with Ricci. The first one is this chi mu rho nu, and there is a second one, a3, r mu nu, chi mu nu, chi. Then there is a fourth coupling with r, and a fifth coupling also with r. Oh, one important thing that you discover when you calculate the Lagrangian by means of the inverse of this object. So you know what you should get in flat space, and then you covariantize it, and you get this thing. Well, one thing that you notice is as follows. The non-massive term, let's say the kinetic term, is in flat space. It coincides with the quadratic expansion of the Hilbert Lagrangian around flat space. So this is the gauge invariant part, if you want. The same way as in the Broca theory, the non-massive part coincides with the one you would get for gauge fields, spin 1 gauge fields in that case. So you have exactly that plus a master. And while in Broca theory it was relatively easy, and that's why we started from the Lagrangian, because we just added the unique master we could write. Here it's less straightforward, because you see we have a mass term that's made of two terms, and only a combination of those two is correct. So if you want to start from a Lagrangian to study the Pauli fields, you should proceed as follows. You write down the quadratic part of the Hilbert action expanded around flat space, and then you add the most general mass term, which will contain two independent terms, and then you study the field equations and you check when those field equations do not propagate those 5 degrees of freedom, and that will fix uniquely the relative coefficient of the two mass terms. Once you have found that, you can invert it and you will find this unique propagator. So in the end, the solution is always unique, because the requirement is always that you have to propagate only the right amount of degrees of freedom. In this case it is 5. Let's check indeed from the field equations. So in flat space we want to check that the field equations do not propagate more than 5 degrees of freedom. So in flat space we have 1/2 del rho chi mu nu del rho chi mu nu minus del mu chi plus 2 del mu chi del nu chi mu nu minus 2 del mu chi nu rho del rho chi nu minus m squared chi nu plus m squared chi squared. And so the equations of motion are 0 equals. So from here you have minus box chi nu. From there you have the trace. So that gives you, when you take the variation, you have eta mu box chi. Then you have here you cancel the factor 2 because there are two equal terms. Here you cancel the factor 2 because there is a 2 front. So you get minus eta mu from the trace del rho del sigma chi rho sigma. And then when you take the variation of that, you will have minus del mu chi. Now we go to this term here, and here you have a plus. You lose the factor 2 because there is a 2 divided by 2, and you get still two terms because they have to be symmetrized in mu and nu. So the two do not really give exactly the same contribution, but they give the same contribution up to an exchange of mu with nu. Plus del nu del rho chi mu rho. Then the mass here and the mass with the trace. Okay. That is equal to 0. Let's take the divergence. Divergence gives 0 equals. Let us define V mu as the divergence of chi, because we meet it frequently now. So for example, here we have minus box V nu. Plus del nu box chi. Minus, this is del nu, this is the divergence of V. Double divergence of chi is one divergence of V. Minus box del mu chi. Which cancels, this is the first term that cancels something, plus box del rho chi rho plus box V nu, which cancels the other one. So now we get to do these three things. Have to take del mu of this. So that is equal to plus del nu double divergence, which is a simple divergence of V. Then the mass term. Mass term gives V. The second mass term gives del nu chi. And that implies that V mu is equal to del mu chi. So only the last two terms survive, and they give this condition. In particular, if you take the divergence of that, you get box chi is equal to the divergence of V. Now let's take the trace of the equations. So 0 is equal to what? Here you have minus box chi plus 4 box chi, so you have 3 box chi minus 4 divergence minus box chi plus double divergence of chi, so plus the divergence of V, plus another time the divergence of V, so from here, and then minus m squared chi plus 4m squared chi. So that is equal to 2 box chi minus the divergence, minus 2 the divergence, and that's 0 because of what we found earlier, plus 3m squared chi. So that implies that chi is 0, doesn't propagate, but if chi is 0, this thing implies that the divergence of V is 0. And this thing implies that entirely V is 0. Not only its divergence. So let us stress that when m is equal to 0, we have the quadratic part of the Hilbert action. Which has the gauge symmetry that we know of. Delta chi mu nu equals del mu epsilon nu plus del nu epsilon mu. In general, you can also have higher spin fields that are described by completely symmetric tensors with S indices. If you want spin S, one index for spin 1, two indices for spin 2, and they will have, in the massless case, a gauge symmetry of this form. There is a parameter epsilon with one index less, so S minus 1 indices. You have the derivative and you have a complete symmetrization that gives you a meaningful gauge symmetry that can be used to build massless higher spin fields. Unfortunately, massless higher spin fields only exist in the free field limit because they cannot couple with themselves or with gravity. And the reason is that there is a no-go theorem actually. So it's and still an open problem how to get around that no-go theorem. So we have to stop to spin 2. only fields of spins equal to 0, 1/2, 1, 3/2, and 2 can be consistently described by local Lagrangians and then quantized. So let's move on to talk about the Rarita-Schwinger spin 1/2, 3/2 fields. Rarita-Schwinger theory. So the spin is 3/2, and we will only do it in flat space because that is enough already. We will not use spins or fields with spin equal to 3/2 in this course, but we will see that for quantum gravity the Pauli fields action is important. So the Rarita-Schwinger spin 3/2 field in flat space is described by a spinor. Spin 1/2 field is described by psi alpha, where alpha is the spinor index. Well, 4. That's a spinor and a vector with spinor index alpha and a Lorentz index mu. Because this is 1/2, this is 1, so you build a spin 3/2 field by means of something that's both 1 and 1/2, so to speak. Let's write the Lagrangian. The Lagrangian is equal to minus psi bar mu epsilon mu nu rho lambda gamma 5 gamma nu del rho plus m sigma mu lambda psi lambda. What is this sigma? They are still the gamma matrices anti-symmetrized in with this overall factor now. And if you want, we can eliminate gamma 5 and the epsilon tensor using identities for the gamma matrices. So another way to write the Lagrangian is like this. Psi rho minus m psi bar mu sigma mu nu psi nu, where this gamma with 3 indices is a completely anti-symmetrized product of 3 gamma matrices. So that is 1/3 factorial gamma mu, gamma nu, gamma rho plus permutations. But that is anti-symmetrized. So there are minus signs anytime you exchange only 2 indices. So anti-symmetrized permutations. Okay. Or we can write also the Lagrangian in this form: minus psi bar mu q mu nu psi nu, where the quadratic part can be read by expanding this product. So this is a third way to write the same Lagrangian, and this q mu nu, the quadratic part, is eta mu nu minus gamma nu times the Dirac term I del slash minus m minus I gamma nu del mu plus I gamma mu del nu. Okay, so let's recall that the gamma matrices satisfy the Dirac algebra, and what can we do with this object that's both a spinor and a vector? We can, for example, build its divergence, and that is just a spinor. It's not a vector, it's just a spinor. So this has spin 1/2. What can we do also to obtain another spin 1/2? If you contract psi mu alpha with gamma mu, that's also a spin 1/2 field. Now, those two should not propagate, which means that the pole of the propagator should not be there for these components. Otherwise, inside the so-called spin 3/2 field, you would propagate other things that have nothing to do with a spin 3/2, and the representation would be not irreducible. So it's better. So if you want to write the correct action, you have to proceed the way we said. But here we have already given the answer. Again, the answer can be fixed uniquely. So basically, you write down the most generic quadratic part, which should be linear in derivatives and the mass. And then impose the conditions. So the conditions are that those two objects are zero if you use the field equations, or from the propagator point of view, that suitable contractions of the propagators with momenta or gamma matrices will cancel the pole. So let's do it on the Lagrangian. In particular, the equations of motion are just this. And so we want to show that they imply that the objects written above vanish identically. Let's start from the divergence. We take del mu q mu and see what happens. That's certainly, yes. Once we will also contract with psi nu, we will get 0, but for the moment we just study this object. So what is it? So here you get del nu minus del slash gamma nu I del slash minus m minus I gamma nu box, and then you have that, which means plus I del slash del nu. Okay. So let us use the Dirac algebra to exchange those two. and we get del nu plus gamma nu del slash minus 2 del nu, which multiplies I del slash minus m minus I gamma nu box plus I del slash del nu. Okay. Now, what can we do now? It's convenient to isolate the mass term, which will be the only one which will survive, although it's not straightforward to see that the rest cancels out. So we isolate the mass term and then we write the other ones. The mass term is minus m, and that multiplies del nu minus 2 del nu is minus del nu. So gamma nu del slash minus del nu. Gamma nu del slash minus del nu plus. There is an I to collecting every other term. So here we have the slash. The slash gives the slash is box. Let's recall that the slash squared is box. So these two give gamma nu box. Then we have minus partial nu partial slash. And then the other two terms, so plus, or actually minus, box minus box gamma nu plus the slash partial nu. Partial slash partial nu. Okay, so we see that these two cancel as well as these two, and we get what? So this implies that this object is 0 when it acts on psi nu, and that means this. So this is the condition we find from the argument that we have just given. Another condition can be found by means of this contraction. And what is it? Let me check a moment. Battery 19. Okay, so gamma mu q mu nu is the other contraction that we want to study to mimic those two objects. So if we contract here, we have gamma minus 4 gamma. That's minus 3 gamma. Minus 3 gamma nu I partial slash minus m. Then we have contracted with gamma. Here we have minus I partial slash partial nu. partial slash not partial nu gamma nu plus 4 gamma mu is equal to 4 I partial nu. Let's isolate again the mass term, which will be the only one to survive at the end. So 3m gamma nu. Then there is an I that we can collect. Let me write first the last term 4 del nu. Then there is minus 3 gamma nu partial slash minus partial slash gamma nu. Okay, that is equal to 3m gamma nu plus I 4 partial nu. Then we have to exchange those two as usual. So we have plus 3 partial slash gamma nu and minus 6 partial nu minus partial slash gamma nu. Okay. And then we have 3m gamma nu plus what? Just a sec. So I have to plug in there we go. So we have plus I so what do we have here? So we have a minus 2 del nu from here. Then we have plus 2 del slash gamma nu. Okay, let me collect factor 2 in front. Let me also oh yes, this is wrong. We have partial slash gamma nu. So, okay, let me rewrite this the nice way. Factor 2 I partial slash gamma nu, yes, minus del nu. And yes, something we did not show earlier is that this is also 0. See, this thing is a little bit different, but we can show that this is 0 as well. How to do it? So we can write this term by exchanging the order of partial slash and gamma nu by means of the Dirac algebra, and you get that. Then the two terms there give minus partial slash gamma dot psi plus 2 the divergence. And therefore we also have divergence equals 2 divergence minus this object. Rearranging, partial slash gamma dot psi is equal to the divergence. So when you act with psi nu here, you have partial slash gamma dot psi minus the divergence. That means that this thing goes away. So gamma mu cum mu nu psi nu equals 0 implies what? That this is 0 on psi. Gamma nu psi nu is 0 when we act on this psi nu. So it implies gamma dot psi equals 0. But if gamma dot psi is equal to 0, here, you also have that the divergence is equal to 0. So we have proved that this quadratic Lagrangian on shell does not propagate either of those two, and in the end it is the right action to propagate just the massive spin 3/2 field.